Welcome back, Night Owls. This is Dr. Nighttime. And tonight we're going to do something a little different. Tonight I'm going to go through a mock exam that I've come up with that covers series, sequences, Taylor series, power series, or that particular topic from the end of Calc 2 or the end of Calc BC. And the reason I decided to come up with a mock exam on this particular topic is because of the nature of how you should go about trying to solve the problems. This isn't the sort of thing where you have your list of rules and then you look at a problem and you immediately know which rule should apply, right? You've got a bunch of different rules to choose from, and you have to mentally think about, well, which of these is going to work, which is going to be useful. And there are all sorts of techniques for figuring out what to try to do. And for that reason, using the end of section or end of chapter exercises in the textbook that are usually segmented by topic, that wouldn't really work. Because if I were to tell you, hey, use the ratio test to determine whether or not this series converges, right? Well, if I told you to use the ratio test before even asking the question, that kind of gives away a big part of how you're supposed to solve this. So instead of that, this is just a bunch of questions all mixed together. Quick note. Right? So yes, this is a mock exam. Right? I'll read the title sheet off. Right? This mock exam was never meant as an actual exam, but as a study guide. Follow this property of Dr. Nighttime Tutoring. It may be freely distributed to anyone. Right? Mock scoring note. Some of the harder questions have hidden bonus points. That is, fully solving these problems would have awarded more than the stated number of points, while some incomplete work could still have scored full credit had this been an actual exam. A couple of other notes that I forgot to put on the cover sheet here. This exam was designed to be completed in about 2 hours. And it was designed to be completed pen and paper without use of a calculator. Some of the problems there, if you had use of even just a standard 4-function calculator, well, a standard scientific calculator at least. Right? Anyway, some of those would have been significantly easier and would skip the entire series portion of this. So, pen and paper, no calculator allowed, about 2 hours. Anyway. So in part 1, determine whether each of the following series converges or diverges. And converges absolutely, converges conditionally, or diverges. You have first series sum as n goes from 1 to infinity, cosine pi n over 2 to the n. Question 2, sum n goes from 1 to infinity, 1 minus 1 over n all to the n squared. Question 3, sum n goes from 1 to infinity, negative 1 to the n, sine of 1 over n all over square root of n. Question 4, n goes 1 to infinity, negative 1 to the n, 5 to the n over n factorial. And question 5, sum n goes 1 to infinity, negative 1 to the n. A fraction, numerator is n squared plus 4n plus 4, denominator is n cubed plus 3n squared plus 6n plus 7. All right. Again, feel free to pause here, work some of these out. I'm going to go through all the questions, though, before going into the solutions. Part 2, more of the same, but now there's the added rule, if it converges, find the limit. And we have 1 over n squared plus 6n plus 8. Another one is sum n goes 1 to infinity of cosine 1 over n over n. So it's cosine of 1 over n, that whole thing over n. Question 8, sum as n goes from 1 to infinity of n over 5 to the n. Question 9, sum as n goes from 0 to infinity of negative 1 to the n times 1 over 2n plus 1. And question 10, sum as n goes from 2 to infinity of 1 over n ln n. And you might want to think about why I'm starting at 2 instead of 1 there. Part 3. For which values of x do the following series converge? 5 points each. Sum as n goes from 0 to infinity of x to the n over n, and sum as n goes from 0 to infinity of x minus 3 to the n over 2 to the n times n squared. Hi, quick interjection here. A minor correction. Those two series from right there, they should have started at 1 rather than 0. If you start at 0, you're going to get zeros in the denominator. Yeah, that shouldn't work. So no, start them at 1 rather than 0. Thank you. Now back to our regularly scheduled programming. So thus far we've seen 50 points worth of stuff. Yes, this is nominally out of 100 points, but again, there is some room for hidden bonus points, so the maximum possible score is more than 100. But again, it would be graded out of 100, and then I'm not sure whether I'd need to curve this or not. It would depend. It would probably depend on who was in my class. Like if I were a professor at a school, which school it was. In the imaginary situation that I was a professor at MIT, I could probably not curve it quite as much as in the equally imaginary situation that I was a professor at my local community college. That there I'd probably need to give a bit better of a curve because it's not MIT. Anyway, part 4 for 10 points. Find the following limit. Limit as x goes to 0 of a fraction. Numerator of the fraction is cosine of x squared minus 1 plus x to the 4th over 2. Denominator is e to the x minus 1 minus x squared over 2 factorial minus x cubed over 3 factorial minus x to the 4th over 4 factorial minus x to the 5th over 5 factorial minus x to the 6th over 6 factorial minus x to the 7th over 7 factorial. Yeah, that whole thing is the denominator. Part 5, for 10 points each, estimate the following quantities to the nearest 0.00001. Again, this is without a calculator, pen and paper. One of them is the square root of 99. The other is the integral from 0 to 0.1 of sine of x over x dx. Hi, another brief interjection here. Minor clarification of the phrasing. When I said to the nearest 0.00001, I meant get the answer correct to within 0.00001. Right? If the true answer happens to be like something 5, so that having it off a tiny bit in one way or the other, well, it might round differently. Yeah, we're not worried about that. No, we're saying that the answer you get should be less than 0.00001 away or within that much from the true answer. So we're not worried about the exact direction of rounding. Just make sure that whatever uncertainty you have is that small. Thank you. And so thus far that's 80 points. And finally, part 6. Find the first 3 non-zero terms of the Taylor series centered at 0, so the Maclaurin series of the following functions. For one of them, e to the x times sine x over natural log of 1 plus x. And for the other, it's the same directive, but I'm giving more information here. You've just got some functions f and g, and you know f of 0 equals 0, f prime of 0 equals 1, f double prime of 0 equals 2, f triple prime of 0 equals 3, g of 0 equals 4, g prime of 0 equals 3, g double prime of 0 equals 2, and g triple prime of 0 equals 1. Hi, one last little clarification or correction. For problem 16, the function actually has a hole at x equals 0, so I shouldn't have phrased it as find a Taylor series centered at 0. What I should have said was find the first non-3 zero terms of a polynomial approximation or Taylor series approximation for values of x near 0. Because, yeah, the function and its derivatives don't even exist at 0, so you can't actually do all that. But you can say, okay, let's pretend this hole was filled in, and do it that way. And if you approach this in a standard way, you actually won't even notice that there's a problem at 0. But yes, I should have just phrased that as find a good approximation for values near 0. All right. So that's the exam. Well, the fake exam. I should note that because I work as a private tutor and I work with students from various schools where the instructors have different, might focus on different things. Some might be harder classes, easier classes. It's better to over-prepare my students than to under-prepare my students. So this exam is deliberately chosen to be at the difficult end and hitting on some difficult topics so that students don't feel under-prepared. So I'd be a little surprised if an actual exam were significantly harder than this. I'd be considerably less surprised if a specific exam were considerably easier than this. So I am putting that out there, but again, because of the uncertainty here, I do have to bias this to the more difficult side. Anyway, feel free to pause, work this out as best as you can on your own, and if you want to see the solutions, they're coming shortly. Major spoiler warning. All right, so let's go through some of these problems on just, hey, does this converge? And if so, is the convergence absolute or conditional? All right, so we're starting with this problem 1. Sum as n goes from 1 to infinity cosine pi n over 2 to the n. There are a couple of productive ways to approach this. One healthy way is to look at, hey, look, I've got this cosine pi n. I don't know the details of, cosine of all that many numbers, right? But I do know that it's between -1 and 1. And so I'm looking at something that is no worse than a 1 over 2 to the n or a -1 over 2 to the n, right? So I could say absolute value cosine pi n over 2 to the n is no worse than 1 over 2 to the n. And because the sum of 1 over 2 to the n converges by being a geometric series, right, converges to 1, we know that this, since we took the absolute values anyway, we know it absolutely converges. And so we don't even have to test the original function, right, even with the absolute values, it's going to converge. If we wanted to look at the original function anyway, right, there is another approach. If you're kind of stumped about this cosine pi n of, oh, what do I do with this? And you don't get the idea of, well, okay, it's no worse than 1. That's okay. But let's just start writing out the first couple of terms. When n equals 1, cosine of pi is -1. So I'd have -1 over 2 to the 1 is 2. Okay, the n equals 2 term. Cosine of 2 pi is +1. The denominator is 2 squared, or 4. Okay, the next one. Cosine of 3 pi is -1. The denominator, 2 cubed, is 8. And we realize we have ourselves a good old-fashioned geometric series with ratio -1/2. Yeah, and so this should converge to -1/3. Right? Standard geometric series formula for that. Okay. Question 2. I've got 1 minus 1 over n, and the whole thing is to the power of n squared. All right, when you've got this power of n in your exponent, that's a good indicator that you might want to do the root test. All these terms are positive, by the way, right? For n at least 1. Well, okay, the first one's a 0. We can actually ignore that. Everything after that, these terms are positive. So if it converges absolutely. We don't need to worry about absolute value of anything because they're positive to begin with. Okay? So we can do a root test. Root test ends up being a test for absolute convergence anyway, but let's see what this does. Right? I would need to check the nth root of 1 minus 1 over n to the n squared. Okay, the nth root of the n squared, that's just going to get us 1 minus 1 over n to the n. And what the root test tells us to do is take the limit as n goes to infinity. Hopefully, if you're in a class like this, you recognize this limit as n goes to infinity of 1 plus any constant over n, right? In that case, that constant is negative 1 to the n. Hopefully, you recognize this as limit definition of e or limit definition of e to the x. This, by limit definition, in the limit as n goes to infinity, in the limit as n goes to infinity, will go to 1 over e. If you didn't recognize that. Right? But this particular limit comes up quite a bit anytime you're doing probability or uncertainty. Essentially, you have to know if I've got something that's got a 99% chance of going right, but I'm worried it might go wrong, and I try this 100 times, I'll have approximately a 1 over e chance that it never goes wrong. If I tried it 200 times, it would be a roughly 1 over e squared chance that it never goes wrong. And so this is something that engineers would need to worry about whenever you're testing to make sure that stuff will last a long time, right? You have to say, okay, how long would it take probably for something to make this go wrong? If you didn't recognize this limit, then you could say, okay, I've got this indeterminate form in the limit, right, a 1 to the infinity, and you can take the natural log of both sides, right? If your limit is this much, then you have ln of your limit equals n. I guess maybe I should put the limits in here anyway. I'll take the limit as n goes to infinity. N ln 1 minus 1 over n. And you can solve this either with L'Hopital's rule, or since you know what Taylor series are now, you can realize that 1 minus 1 over n, or ln of 1 minus 1 over n, becomes negative 1 over n plus higher order denominators of n. So you'll have like a plus 1 over n squared minus 1 over n cubed. Right? You'll have higher order stuff there. I guess the 1 over n squared, yeah, I think you get a denominator of 2. The point being, the leading order term here is negative 1 over n. So this will go to negative 1. So natural log of your limit is negative 1. And so your limit is e to the negative 1 or 1 over e. Since 1 over e is less than 1, then this must converge absolutely. If I were grading this for my imaginary students in the imaginary school where I'm the imaginary professor, if you had gotten this as far as doing a root test but not correctly evaluating this limit, that would have been worth 2 points out of 4. All right. Next problem. Sum n goes from 1 to infinity of negative 1 to the n, sine of 1 over n over square root of n. So what you could realize is that for large values of n, sine of 1 over n is decreasing in magnitude, right? You're taking sines of smaller and smaller angles. Square root of n is getting bigger and bigger for larger n. So you've got these terms that are decreasing in size towards 0. So by alternating series, this must converge. And now you have to check absolute or conditional convergence. And this is where it gets a little harder. What you have to remember is that sine of a small angle is approximately equal to that small angle in radians. So you'd have sine of 1 over n is approximately equal to 1 over n. This is the engineering approximation. The more mathematically formal version is limit as n goes to infinity, sine 1 over n over 1 over n equals 1. And this gives you a limit comparison to do. You can compare limit as n goes to infinity, sine of 1 over n over square root n over 1 over n over square root n. And that limit's going to equal 1 because the square root of n's in the denominator is canceled. So if one of these converges, the other one must converge also. 1 over n over square root n equals 1 over n to the 3 halves. You have a p series with p equals 1.5, therefore convergent. You also could have done direct comparison test rather than limit comparison test, by the way. While sine of 1 over n is approximately 1 over n, it's going to be a little bit less. If you remember the exact way that the squeeze theorem works, it's actually a little bit less. They'll approach each other, but for any fixed n, it's a little bit less. So you could say it's less than 1 over n over root n, which converges, and thus prove it converges that way. So again, number 3 converges absolutely. For number 4, negative 1 to the n of 5 to the n over n factorial. This is, I mean, when you see the factorial in the denominator, pretty good giveaway that you either want a ratio test or possibly matching it to some sort of Taylor series. If you had to show what it actually went to, yeah, you might have to do a Taylor series. Here, just do a ratio test. 5 to the n plus 1 over 5 to the n times n factorial over n plus 1 factorial. I guess, generally, if you're doing this kind of early, you'll be told, oh, do 5 to the n over n factorial and divide that by 5 to the n plus 1 over n plus 1 factorial. Realistically, right, by the time you're prepping for a final exam on this, you should know the pattern of pair up the similar looking terms. Right, so the 5 to the n plus 1 over 5 to the n times n factorial over n plus 1 factorial. This gets you 5 over n plus 1. Limit of that quantity goes to 0. So since the ratio goes to 0, this converges absolutely. Right, you can just test absolute convergence and take the absolute values first and solve it that way. And finally, for part 1, sum n goes from 1 to infinity, negative 1 to the n times n squared plus 4n plus 4 over n cubed plus 3n squared plus 6n plus 7. Again, when you think in the long run, for large values of n, approximately how is this behaving? Right, the same line of thought you should have had for sine of 1 over n over square root n. You'd say, in the long run, this behaves like 1 over n. So we limit compare to 1 over n. So in that limit, you compare it to 1 over n, right? N squared plus 4n plus 4, limit as n goes to infinity, n squared plus 4n plus 4 over n cubed plus 3n squared plus 6n plus 7 over 1 over n. Right? That's going to go to 1. So we just have to look at this 1 over n. And so that diverges, right? So it doesn't converge absolutely. And what you can say is that for sufficiently large n, these terms will be decreasing in magnitude going towards 0, right? It doesn't matter whether or not you get some wiggles early on, right? You can say, you know that in the limit, these will be, these fractions, well, so these fractions for n at least 1 will always be positive. Yeah, positive divided by positive. In the limit, they are approaching 0. They behave like 1 over n. So what you can say is they are eventually decreasing. And we know how this function approximately behaves in the long run. So because the terms are eventually decreasing, but they're alternating, this converges by alternating series test. So this must converge conditionally. Okay, part 2. For each of the following series, determine whether the series converges. If so, find the limit. This is where the hidden bonus points are. If you can, on 3 of these, it converges. So 3 of these series converge. To find the limit, you would score the additional 4 bonus points per question for 12 total bonus points available for a maximum possible score of 112. Right? The 100 regular points plus the 12 bonus points. I felt that some of those tricks were even a little too weird for this exam, or for something like this, but I wanted them to be testable, but felt like, yeah, there are some particularly challenging tricks on some of these. Number 6. So this one pretty clearly converges by either direct comparison or limit comparison to 1 over n squared. Right? You can maybe say 1 over n squared plus 6n plus 8 is less than 1 over n squared. 1 over n squared converges because it's a p-series with p equals 2. So this must also converge. Now for the bonus points, what does it converge to? I hope you like partial fraction decomposition. 1 over n squared plus 6n plus 8 equals we don't know over n plus 4. Or let's do the n plus 2 first. Plus we don't know over n plus 4. an plus 4a plus bn plus 2b equals 1, right, because the denominators will just match. You get that the an plus the bn must cancel because there are no n's on the right-hand side. A equals negative b. You have a 4a and a 2b. You can say that that cancels to a 2a, right, because it's 4 minus 2 equals 1 because b equals negative a. A equals a half. B equals negative a half. So now, if we try writing these out, for n equals 1, 1/2 over 3, so we get 1/6 minus 1/2 over 5, 1/10. N equals 2. 1/8 minus 1/12. N equals 3. 1/10 minus 1/14. N equals 4. 1/12 minus 1/16. We could do this all night, except this is designed to be completed in 2 hours. you have to realize is that the positives and negatives cancel. And you have a telescoping series. The 1/6 and 1/8 will never cancel. If we had more terms, these stray minuses would cancel. So you get 1/6 plus 1/8, common denominator 24, 7 over 24. All right, number 7. Cosine 1 over n over n. So here you have to think about how cosine of 1 over n behaves for large n. You're taking cosine of pretty much 0. Cosine of 0 is a 1. So you would limit compare to 1 over n, right? You'd say limit n goes to infinity, cosine 1 over n over n over 1 over n over n's cancel. You get cosine 1 over n over 1. Limit as n goes to infinity. This is going to go to 1. So this will have the same behavior as 1 over n. It's a harmonic series. It diverges. All right. Number 8. We have what looks tantalizingly close to, but is not quite, a geometric series. Right? N over 5 to the n. So, first, does it converge? Yes. Again, you've got the 5 to the n, ratio test, n plus 1 over n times 5 to the n over 5 to the n plus 1. Again, maybe you would want the stacked up fraction of n plus 1 over 5 to the n over n over 5 to the n plus 1, but it's good practice to recognize where the similar looking terms are going to be. And in the limit, this just goes to 1 over 5, right? N plus 1 over n goes to 1, 5 to the n over 5 to the n plus 1 goes to 5. So it's going to converge. Regular points scored. Now, how do you get the bonus points? For this one, you have to remember one of the ways, that algebraic way of finding sum of a geometric series. You have to do that trick, and you have to do it twice. Right? This is going to be 1 over 5 plus 2 over 25 plus 3 over 125 plus 4 over 625. That's going to equal x, right? Where x is going to be your sum. Normally, you would multiply or divide by 5, cancel, subtract one from the other, and you just have your answer. Let's multiply by 5 just so that our denominators aren't quite so weird. 1 plus 2 over 5 plus 3 over 25 plus 4 over 125 plus 5 over 625, right, because that's somewhere in the dots, equals 5x. To keep our numbers positive, let's subtract the top equation from the bottom. Now we get 1 plus 1 over 5 plus 1 over 25 plus 1 over 125 plus 1 over 625. We get the idea, equals 4x. Now you've got a choice. You could recognize that with the geometric series sum, that 1 plus a fifth plus 1 25th, etc., is going to go to 5/4. Or just do it again. Right? Multiply by 5 again. 5 plus 1 plus 1 over 5 plus 1 over 25. We see where this is going, equals 20x. Subtract again. 5 equals 16x. X equals 5 over 16. So again, it's just the two-step approach for geometric series. You do the trick you would do for geometric series, and you just do it twice. Number 9. Okay, this, of all the questions that could absolutely freeze you, and you get to a point where you just have no idea how to proceed, this is the one where you would have the least, you would feel the least embarrassed, or you should feel the least embarrassed for not seeing how to proceed, right? For the regular points here, right, okay. It converges, right? Alternating series test, right? It's an alternating series. The terms are decreasing. That, yeah, you should feel a little embarrassed if you don't see it. No, I mean the bonus point. Okay, so we know this converges, which means, according to this question, we have to find what it converges to. Right? For n equals 0, you've got a 1 minus a third plus a fifth minus a seventh plus a ninth. None of the, like, this isn't a telescoping series. This isn't a geometric series. So what's the only other rule where you could say, it's going to converge to this quantity? If it's a Taylor series, and you plug in the specific value of x. If you happen to remember that the Taylor series for inverse tangent of x equals x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So now if you plug in x equals 1, inverse tangent of 1 minus a third plus a fifth minus a seventh. Oh, look, it's our series. And the inverse tangent of 1 is just pi over 4. Yeah, that, don't feel too bad if you missed that. Lastly, for this section, sum at n goes from 2 to infinity of 1 over n ln a. Okay, why didn't I start the series at 1? Because the natural log of 1 is 0, and if I did that, there would be a 0 in the denominator, which we don't want. And as for determining the convergence or divergence here, right, so it's smaller than a 1 over n, right, so we can't compare that, right, because it's smaller than something that converges. We can't do a direct comparison. Limit comparison isn't going to work, right? It's going to be a lot smaller than 1 over n. It's integral test, right? Well, we haven't done integral test yet, right? That's something that's going to try to cover like everything. Makes sense that, oh yeah, that's a thing. Integral from 2 to infinity of 1 over x ln x dx. A little bit of u substitution. Okay, du equals 1 over x dx. Integral from ln of 2 to ln of infinity of 1 over u du. This is going to equal natural log of infinity minus natural log of 2. Or I guess, if you want to be proper about your improper integrals, you say integral from 2 to upper bound b and take the limit of b goes to infinity. Either way, your upper bound goes infinite. Right? Or so ln of large number is still large. I mean, if it's really, really, really large, it can get as large as you need it to, eventually. So the integral diverges, so the sum must diverge. Alright. On some more normal stuff, I'd say that part 3 probably has the most normal questions on here. Just for which values of x do the following series converge? So, okay, these are power series. Hopefully you know to do a ratio test when you're doing power series. Okay. Need x to the n plus 1 over x to the n times n over n plus 1. Again, this is how I want you thinking about ratios of stuff with fractions already in them. Match up your corresponding terms. This absolute value has to be less than 1. That's going to get you x. And yeah, we're doing limit as n goes to infinity. Right? So we get absolute value of x less than 1. X is between 1 and negative 1. And then you test the endpoints, right? If x equals 1, sum. And I just realized there was a typo in here. These needed to start at 1. After I made such a big stink earlier about the problem on the previous page starting at n equals 2. So yeah, sum as n goes from 1 to infinity. Sorry, we just said that x equals 1, so that's going to be 1 over n. Diverges, it's a harmonic series. If x equals negative 1, sum n goes from 1 to infinity of negative 1 to the n over n. Converges, it's an alternating series. Converges by alternating series. So you would say I put the negative sign on the wrong one, right? X cannot be bigger than 1 but less than negative 1. It kind of doesn't fit that way. But either way, yeah, so the overall rule will be x has to be less than 1 but can be equal to negative 1. And then we do something similar for number 12, right? Little ratio test again. Absolute value of x minus 3 to the n plus 1 over x minus 3 to the n times 2 to the n over 2 to the n plus 1 times n squared over n plus 1 squared. This has to be, or well, in the limit of large n, this has to be less than 1. All right, we get x minus 3 over 2. N squared over n plus 1 squared just goes to 1, so that in absolute value has to be less than 1. X minus 3 over 2 between 1 and negative 1 this way this time. Multiply across by 2. It doesn't change the direction of the absolute values. Add 3. X is between 1 and 5. Check the endpoints. X equals 1. You get sum. N goes 1 to infinity. Negative 2 to the n over 2 to the n times n squared. Converges because it's an alternating series. Well, alternating series with decrease. It passes the alternating series test. For x equals 5. Sum n goes from 1 to infinity. 2 to the n, right? 5 minus 3 is 2. Over 2 to the n with an n squared in the denominator. That becomes 1 over n squared. It's a p series. It converges. P equals 2. All right. Then there's this. You can try to plug in 0. However, you'll get 0 over 0, right? And before taking this section, before studying this chapter, you would have thought, okay, do L'Hopital's rule. And that will eventually work. If you want to do a L'Hopital's rule 8 times, that means taking 8 derivatives of cosine of x squared. Bear in mind, after one round of that, you're doing chain rule. So you have 2x times negative sine x squared. Now you've got a product rule to do a 7th derivative of. And you're going to keep getting more powers of x on some of those. If you did 2 rounds of L'Hopital's rule and then gave up, you would have gotten 5 out of the 10 points. Meanwhile, since we know a thing or two about Taylor series, at least we hope to, Taylor series expansion of cosine x squared, 1 minus x squared, or sorry, 1 minus x squared squared, right? You square what's inside, so x to the 4th over 2 plus x to the 8th over 24 minus the 1 plus the x to the 4th over 2. And in our denominator, we would have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. We kind of have to recognize that everything through the 7th power is going to cancel out. So in order to get anything meaningful, we have to go all the way out to the 8th power. It takes longer to write this down than it does to realize it. Almost done. Minus 1 minus x squared over 2 factorial minus x cubed over 3 factorial minus x to the 4th over 4 factorial minus x to the 5th over 5 factorial minus x to the 6th over 6 factorial minus x to the 7th over 7 factorial. Okay. Most of these cancel, right? Everything cancels except for the x to the 8th over 24 over x to the 8th over 8 factorial. Right? Notice that, oh yeah, I guess I should have had the plus dots here for more stuff in the Taylor series, but we'd realize that since we're taking the limit as x goes to 0, the higher ordered powers of x become least significant. X to the 8th over x to the 8th cancel, or so we can say x to the 8th over 24 over x to the 8th over 8 factorial. This is going to be 8 factorial over 24. Now remember, this was a non-calculator thing. We can write this as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Dividing by 24, we can write 24 as 8 times 3. Cancel, 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 cancel. 5 times 2 times 1 is 10. 10 times 4 is 40. 7 times 6 is 42. 42 times 40. 1600 plus 80. Right, 40 times 40 is 1600. 2 times 40 is 80. 1680. Okay. Maybe the arithmetic there was a little tedious. Definitely 9 out of 10 if you did all this and got bungled on the arithmetic. But yeah. So no, you don't just look at it and say, 0 over 0. L'Hopital's rule. If it doesn't work, L'Hopital is even harder. Because I'm not sure how much I'd enjoy watching someone try that. I'd probably get bored before the person I was watching got frustrated. Unless the person was entertaining me with his or her frustration. Anyway. More arithmetic. This is not as bad as the, well, I guess the 1680 stuff wasn't that bad. Okay. Square root of 99 without a calculator to this many decimal places. More Taylor series. We recognize this as square root of x, right? We could say f of x equals square root of x. And we want to try to evaluate this at x equals 100, right? So we'd say f prime of x equals 1/2 x to the negative 1/2 f double prime of x equals negative 1/4 x to the negative 3 over 2 f triple prime of x equals 3/8 x to the negative 5 over 2. So we could say f of x becomes approximately, right, yeah, if we center this at 100, right, that's the logical place to center this. It's a number whose square root we know. We could say square root of 100 plus x minus 100 times 1/2 100 to the negative 1/2 yes, minus, right, minus because we've got a negative over here, minus x minus 100 squared over 2 times 1/4 100 to the negative 3 over 2. Right? We'd say it's approximately square root of 100 is 10 minus 1 over 20, right? 1 over 2 times 1 over 10 minus 1 over 8 times 1 over 1,000. the next term would end up being approximately 3 over 8 over 100,000. Oh, divided by 3 factorial, so divided by 6, right? So now you've got this tiny little thing. And you know that the error bound is the worst case scenario next order derivative. And so you know that this next term, everything else you're going to be adding in, is going to be not as bad. It's going to be smaller. Right? So your error is going to be less than this 1 over 100,000. Right? We want this in decimal form. 10 minus 0.05, right? That's 1/20th, minus 1 over 8,000, less than a tenth, less than 100, less than 1,000th, 1 over 8,000, 125. We would get 9.94987.5. I guess the nearest point 0, 0, 0. Yeah, it was 0, 0, 0, 0, 0, 1. Yes, so this would be our best guess. And if you were to, after the exam, compare on the calculator, square root of 99, yeah, 9.9498743 something, right? So it was to the nearest, right? You're off by less than 0.000001. Perhaps I should rephrase this as to within 0.000001. Yeah. Anyway. So that's that one. Okay. Then, integral from 0 to 0.1, sine of x over x dx. If you're trying to find an integral of sine of x over x dx, just integral that function manually, give up now. There is no such algebraic function. Right? It becomes one of those special functions. So what do we do? Oh, one thing we have to worry about, possibly, is, oh no, we have an x in the denominator, and x is starting at 0. Does this mean that we have an improper integral? And no, it doesn't. Limit as x approaches 0, sine of x over x is just 1. Right? So we've got this function that's approaching a 1. Yes, it briefly disappears at that one little hole, but that's okay, right? That's not going to affect the area, right? You've got a tiny little thread missing. All right. So instead, what do? Well, this is the Taylor series test. So it's the exam that covers Taylor series. So let's approximate this with Taylor series. Integral from 0 to 0.1 of x minus x cubed over 6 plus, now remember, sine of x, or well, yeah, so plus x to the 5th over 120, over x. Integral 0 to 1 minus x squared over 6 plus x to the 4th over 120, dx. X minus x cubed over 18 plus x to the 5th over 600, between 0 and 1. At 0, these all go to 0. 1 minus 1/18. Sorry, between 0 and 0.1, 1 minus 0.001 over 18 plus 0.00001 over 600. We have an alternating series here, by the way. In an alternating series, right, well, one of those convergent alternating series where each term is larger in magnitude than the term that comes after it, the error after you stop is bounded by the next term. So since this third term is actually smaller than our error, we can stop after only these two terms, right? We get 1 minus 1 over 18,000, right? 1 minus 0 point less than 1, less than a tenth, less than 100th, less than 1,000th, less than a 10,000th. And then since 1 over 18 is like 0.0555, right? So 5, 5, 5, 6. We can say that this will be 0.99994 when rounding. Hi, one last correction here. I'm not sure if you caught it as you were following along, but in my solution, when I noticed that the upper bound was supposed to be 0.1, not 1, yeah, in that first term, the term with the biggest number, the most significant term, I forgot to actually do that. So it shouldn't have, the leading term should not have been a 1 minus all that stuff. It should have been 0.1 minus all that stuff. So that the final answer shouldn't have been 0.99994. It should have been 0.09994. Naturally, I gave numbers, like going 0.1 and basing it around 100, where you've got those powers of 10. Yeah, that was deliberately chosen to be easy to do by hand. Yeah. And then the final part. Finding the first three non-zero terms of the Taylor series centered at 0 for each of the following functions. Number 16, I would say number 16 is probably the one that takes the most work to do. So, okay, here's what you do not do. You do not find the function value. So you realize that the function value is 0 because, or so if you're plugging in at x equals 0, I guess, yeah, if you plug in at x equals 0, come to think of it, you're dividing by 0. Does that mean that you can't actually center it there? So hopefully there's not a technical issue with that, because, again, the function has a hole at 0. Perhaps I should have fixed that now that I'm thinking about it here. But if you were to just go through and just find, essentially you're finding an approximation for the function, right? So that the hole itself doesn't really matter. So yes, I should have made this ln of 2 plus x. And seeing what that did. But this is a matter of recognizing known Taylor series and expanding it out. And also realizing, okay, I'm going to start with a 1. Anytime I go beyond an x squared, I can just stop in my Taylor series and work with that later, right? So I've got, for e to the x, 1 plus x squared over 2, dot, dot, dot. For sine of x, I've got x minus x cubed over 6, dot, 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 right? Even the x cubed over 6 is going to be more than I really need. Or, well, kind of. We'll see what happens here. We're going to realize why we were going to need that. For ln of 1 plus x, we have x minus x squared over 2 plus x cubed over 3. Okay, we can divide numerator and denominator by x. So I'll just continue my work down here. 1 plus x squared dot dot dot. 1 minus x squared over 6 dot 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 over 1 minus x over 2 plus x squared over 3 dot dot dot. I have 1 minus stuff. So I can express that as a geometric series, right? I can say dividing by that is the same as multiplying by 1 plus this stuff I'm subtracting plus the square of the stuff I'm subtracting. Right? So I can say 1 plus x squared, 1 minus x squared over 6, 1 plus, now this stuff here is going to be x squared over 2, or sorry, no, x over 2 minus x squared over 3 dot dot dot. Right, anytime I go beyond x squared, I can just have dots. Plus the square of this stuff. That's going to be an x squared over 4, more dots. Okay, and then I just FOIL this out. You could either do term by, you could either do pairwise, or we could realize, all right, what's going to get us a constant? The only way we have to pick something from each factor, so 1 times 1 times 1 is going to get us a 1. That's the only way we can get a constant without an x. Linears in terms of x. I can do 1 times a 1 times the x over here. I can try 1, but then I can't multiply by an x, and I have this x times 1, so plus another x. And then for my x squared, I can do 1 times these x squareds, right? So 1 times negative x squared over 3. 1 times its positive x squared over 4. Okay, that gets me all the 1 times 1s. This 1 times this negative x squared over 4, over 6, has to be times 1, so I'll have minus x squared over 6. Okay, that's all we can do with starting with a 1, right? We can start with a 1 and hit a 1, and these x squareds, I can start with a 1 and hit those x squareds and hit other stuff. Okay, if I start with an x, I can't multiply by anything here to get me an x squared to hit this 1, so instead just x times 1 times x over 2, so I'll say plus x squared over 2. And I can say this x squared, that's the only thing this x can hit that lands with a power of x squared, or a multiple of x squared. And this x squared can hit these two 1s. Plus higher order stuff. Combining our like terms, 1 plus 3x over 2, and then x squared gets multiplied by negative a third minus a sixth is negative a half, plus 1/2 is, plus 1/2 is, oh, sorry, I forgot about this over 2 here. All right, I was going to say this doesn't feel like the same answer I got before, but yeah. Yes, yeah. So we've got x squared over 4 plus x squared over 2, right? Again, the x squared, negative x squared over 3 minus x squared over 6 plus this first x squared over 2, they cancel. We get a 3x squared over 4. And those are the first 3 non-zero terms. And finally, for number 17, if I want the first 3 non-zero terms of the Taylor series expansion centered at 0 of f of x times g of x squared, f of x is going to be 0 Since the derivative is 1, we'll get plus 1x. Since, sorry, plus 1x. Second derivative is 2. 2 over 2 is 1, so we'll say plus x squared. 3 times x cubed divided by 3 factorial, so that's going to be plus 3 over 3 factorial is 3 over 6, that's 1/2, so x cubed over 2. Right. Hopefully you remember how to take your Taylor series. Right. Again, first derivative gets multiplied by x, second derivative gets multiplied by x and divided by 2 factorial, third derivative gets multiplied by x cubed and divided by 3 factorial. Okay, now g of x squared, we're letting x squared be the variable. We're going to have 4. We're going to have plus 3x squared, and then anything after that is going to have x to the fourths in it. Those x to the fourths would be multiplied at least by x's. Perhaps I should have some dots here. But the point is, when you multiply these out, right, whatever's x to the fourth or higher, we don't care about. Yeah, and so now we just multiply across, right? What gets us an x term? This x times this 4. What gets us an x squared term? This x can't actually hit any odd powers of x. This x squared hits this 4. What gets us an x cubed term? This x times this 3x squared is going to be 4x. Sorry, it's going to be 3x cubed. This x cubed over 2 times this 4 is going to get us 2x cubed. So 2x, so we'll say plus 3x cubed for the first one, plus 2x cubed for the second one. And we get 4x plus 4x squared plus 5x cubed. Why not 3x cubed? There we go. Yeah. Yeah. And those are the first 3 non-zero terms. Of Taylor series for the function 17. Anyway, so that's the solution set to the exam. Again, the fake exam. The exam I would have given, which I'd have to make sure to correct some of these, but took about an hour to explain. Now, granted, I wasn't necessarily writing down every single step, but I was explaining in a little more detail than you'd have to write out. But yeah, again, for a 2-hour exam, I feel like in terms of length, this is fine. Again, the difficulty very well may be harder than what most of you would encounter in an actual class. But as always, I hope you found this useful. Until next time, this is Dr. Nighttime wishing you a good night.